Okay, to recap, we have in the top section a system of linear equations, and we converted that system into an augmented matrix where our a variables are our constant times a common vector of our x variables, which is equal to our common vector corresponding to the b values. And we then converted this augmented matrix into this simple equation where A is our coefficient matrix of the system, as well as X and B being our column matrices. Now that I've got you guys a little caught up, let's start with an example where we solve a system of linear equations using what we learned from multiplying matrices. So we have A, X, and B. For B, we know that it's a column vector full of zeros, and so forth and so forth. So we got that out of the way, and we can convert A into an equation, where A is simply just, it's x1 minus 2x2 plus x3 is equal to 0, and we have 2x1 minus 3 plus 3x2 minus 2x3, which is also equal to 0. And given enough practice, what happens next, everyone? And if you said that we converted into an augmented matrix and apply Gauss-Jordan elimination, you are correct. I'm gonna spearhead through that process, and our post-Jordan elimination matrix ends up looking like this. Quick side note, if you have a calculator that can do matrices, especially Gauss-Jordan elimination, determinants, operations, that would be a great investment to make when you're taking linear algebra, because depending on your professor, you may not always work with such kind of matrices. Unless you like the hustle, that'd be my guess. So, back on track, we have acquired the Gauss-Jordan elimination addition of the matrix, and from here we can see that the system has infinitely many solutions. So here's what we're going to do. Let's say we have x1 is equal to t. What does that imply for our other matrices? Well, if we plug t for x1, we get x2 is equal to 4t, and what after getting that for x1 x2, what does x3 equal? Go ahead and pause and figure that out. And if you said that x3 was equal to 7t, you'd be correct. And of course, this is implying that t is any real number. So, let me elaborate on how we found these parameters, since this system has infinitely many solutions. So if we let x3 equal to 7t, and by the way, we probably should have started with that, would have made the process a lot easier. If we let x3 equals 7t, in the second row of our Jordan elimination matrix, that simply becomes x1 times 0 plus x2 plus negative 4/7 times 7t, which is equal to 0. The 7's cancel out, and as a result, you get x2 plus negative 4t, which is equal to 0. And if we solve for x2, we get 4t. And because we have the value of x2 and x3, we could then use it to find the solution for x1, or in our case, the parameter for x1. And yeah, let's do that. Let's plug in the value for x3 for the first row, where we have x1 plus 0 times x2 plus negative 1/7 times 7t, which is equal to 0. 0 times anything is 0, so we just get x1 plus negative 7t, which is equal to, the 7's cancel out, so you just get negative t. And as a result, x1 becomes t. So I hope this actually clears up the quote-unquote solution for this system. So we have our parameters, and in matrix terminology, this is simply just the equation from when we first started this video, which is 1, negative 2, 1, 2, 3, negative 2, times the column vector of x1, x2, x3, and the column vector consisting of zeros. And we've already deduced our x values as parameters. We have x1, 2, and 3. Let's substitute our x variables in terms of t. And as a result, we end up getting t, 4t, and 7t. And we can then go above and beyond and factor out the t in the column vector. So let me just duplicate this, save some time, and we get t times 1, 4, 7. And that is our column vector right there. So in the original problem, we were supposed to solve the matrix equation, and what that implies is just find the x values, and we overdid ourselves. So let me ask a question. What are our solutions to this matrix equation? And if you said that x was x1, x2, and x3, which is equal to t times this column vector, you would be correct. And remember, t can be any scalar. That is, any scalar multiple of the column matrix on the right is a solution. And there you have it. We have now integrated matrix multiplication into systems of linear equations. Congratulations, everyone.